Okay, so as I said last time, we are going to begin a new chapter, and this chapter is now uh, it has to do with Fourier analysis, but it's no longer series, but rather something called Fourier Transform, right? So if you recall from the Fourier series analysis, we said that we can uh, analyze periodic signals and break them up into a superposition of complex periodic exponentials. Complex periodic exponentials that are harmonically related. So if omega naught, for example, is the fundamental frequency, is the frequency for the periodic signal, then we can break down the periodic signal into a composition of exponentials which have frequencies omega naught plus minus so plus minus omega naught, plus minus 2 omega naught, plus minus 3 omega naught, and integer multiples of omega naught, right? So those are harmonically related exponentials, right? What we are going to do now is try to extend the same set of ideas to aperiodic signals, so signals which are not periodic, right? And that's also one of the contributions that Fourier made. And the way I'm going to go about this, as the textbook does as well, is to try to derive the Fourier transform relationship by looking at the analysis for Fourier series first and trying to generalize it for aperiodic signals, right? So I'm going to start this out with this particular example that you see on your screen. So you have, um, oops, correct. There you go. Okay. Acha. So the idea is, so what you see on your screen is a periodic square wave, right, which has a period of capital T, and is this the signal is equal to 1 for all values of capital small t is less than t1, right? And um, and it periodically repeats itself with the period of capital T seconds, right? And then we found out what the analysis, through this analysis, that the Fourier series coefficients turn out to be equal to this, right? So let me just try to briefly, do some analysis here and say, this implies k a k times capital T is equal to 2 sine k omega naught t1 and divided by um, k omega naught. And I can therefore write that this a k times t is actually equal to some function which is a function of omega, and this is omega times t1 divided by omega, where I can just replace omega with something equal to k omega naught. So as k changes, so I just plug in k omega equals k omega naught into this expression. I'm going to get the Fourier series coefficients multiplied by the time period. Okay. Now, if just looking at this in the frequency domain, right? So let's take an example, and this example is k t1 is equal to 2 pi, and the reason why I choose 2 pi is so that things become are going to be easier to understand. So t1 equals 2 pi, and the time period t is 4 times t1, right? Is 4 times t1, and this implies that the omega naught, which is frequency, is 0.25 radians per second, right? Omega naught equals 0.25 radians per second. Now, if I were to plot the Fourier series coefficients as a function of frequency omega, right, what I would get is something like this, right? Something like this. So where what I have here is on the x-axis, I have omega, which is the frequency. And on the y-axis, all I've done is I've just plotted using MATLAB T times A sub K, right? Where this is the frequency 0, this is the frequency omega naught, this here is the frequency 2 omega naught. Similarly, this is 3 omega naught, and so on and so forth. So this is 4 omega naught, and so on and so forth, right? Similarly, this is minus omega naught, this is minus 2 omega naught, this is minus 3 omega naught, and so on and so forth, right? Now, what does these coefficients mean, by the way, right? So if when I say that A naught times capital T is equal to this some value here, that means that the DC component has a contribution equal to this, right? Or as proportional to this, right? Similarly, the contribution because of the complex exponential, which is e raised to the power j omega naught t, uska jo amplitude hai, uski jo contribution hai, is proportional to whatever the height of this element is, right? And what I've done is on the x-axis, I now have the frequency, right? So that means that omega naught, which is actually equal to, as I just noted earlier, is 0.25, right? 0.25 radians per second, ka jo complex exponential hai, that has a contribution equal to this. Similarly, so this is 2 omega naught. This is here is so this is 0.5 radians per second, and so on and so forth, right? So this visualization, what this visualization tells me is that as the frequency increases, right, what is the contribution of that frequency? So this is what that visualization tells me, right? And these coefficients, they are equally spaced on a function which is actually this function, right? Is function ko equally maine sample kar liya, and this function is actually the red function here, right? And that is equally spaced at omega naught, at 2 omega naught, at 3 omega naught, and so on and so forth. Uske samples mere paas maujood hai, and the samples, they tell me what is the contribution of those frequencies, right? Now, what happens? So here's a question for you. What happens as capital T increases? What if I increase this capital T from 41 to 81? So kya hoga? If I increase the time period of the periodic signal, how would you expect this plots to change? Ji Ibrahim.
जी सर, आई थिंक एक तो हाइट इंक्रीज हो जाएगी, सारे आपके हर ग्राफ की टोटल हाइट इंक्रीज हो जाएगी हर पॉइंट पर, और फ्रीक्वेंसी कम हो जाएगी, श्रिंक हो जाएगा सर, हाइट इंक्रीज हो जाएगी क्योंकि AK into T कर रहे हैं, इस वजह से आई थिंक.
Okay, that's an excellent observation, but there's a slight bit of misunderstanding here. The reason why we actually multiplied with T and plot this as a function of T times AK is so that the height becomes independent of capital T. Ibrahim, unmute kar lein, zara thodi si baat clear kar lete hain, right? So T times AK, remember, is equal to this value here.
जी सर.
Right? And this capital T यहाँ पे कहीं नहीं आ रहा इस height में, right? If there's no capital T here, that means okay, no matter how much of an increase I have in the capital T, this right side is not going to change, and therefore the height is not going to change.
Okay, sir.
Right? Yes. Now, there were other points made, which was the graph compressors, right? So I think Ibrahim, आपने भी बोला था, लेकिन let me go to Daniel. You said graph compressors. What do you mean by that?
Sir, T बढ़ाने से omega naught की वैल्यू कम होगी ना?
हाँ, तो exactly.
ये हो जाएगा 0.125 readings per second, यानी कि 1 सेकंड के अंदर 8 omega naught आ जाएंगे.
Excellent, excellent. So as I increase capital T, omega naught decreases, right? If omega naught decreases, that means the spacing here, or let me use another color. The spacing here is going to decrease, right? So this is going to decrease as omega naught increases, right? And that's what I think everybody else meant. Asad, Khalid, Nusman, Nadeem, good, right? Okay, as omega naught increases, the spacing between the adjacent samples is going to decrease. Okay? And that's exactly what we observe. Let's look at this. So this is the case where T1 is the same 2 pi, but capital T is equal to 8 times T1, right? So it's 8 times higher. And therefore, what would omega naught be? So क्या होगा omega naught? Right, so omega naught here would be equal to 2 pi. Right, so is going to be equal to 2 pi divided by t, okay? And therefore this is going to be pi is 1 by 8, right? So this turns out to be equal to 0.125 radians per second. Okay. Right. So Talha, we are, like I said in the very beginning, we're talking about Fourier transforms, right? And Fourier transform apply to aperiodic signals as opposed to Fourier series, which applies to periodic signals. So we're trying to make a connection between how do we generalize Fourier series for aperiodic signals, right? And that's where we're headed. Right? That's where we're headed. Right. Now, as I increase capital T, right, my frequency increases, right? And as people rightly pointed out, you're now going to have samples which are much, much closely located, right? But what happens in the time domain? What happens in the time domain as capital T increases? Right, so Talha, आप ही बता दें चले.
Omega naught decreases.
Like in the time domain. I mean, what does the graph, I mean, what happens to the graph?
इसकी shape change होगी है.
Shape कैसे change होगी? Right. So as I increase capital T, that means this is going to the right, right? इसका मतलब the spacing between these two increases.
Yeah.
As T increases, T goes up. Right. So it's as Muaz said, as Hassan Shabi. So time axis में expansion in the sense के exactly time से इसमें exactly expansion नहीं है क्योंकि T1 उधर ही रह रहा है. But the pulse, the adjacent pulse, you increase the spacing between the adjacent pulses, and that corresponds to increasing the time period. Okay? And what happens as I increase the capital time period, frequencies may harmonically related and because they become closer and closer together, right? So it's the first one, so this would be 0, right? And this would be omega naught. This would be 2 omega naught. And this here is now 4 omega naught. And this, by the way, is still 0.5 radians per second as it was earlier. Right? Except that 0.5 radians per second, 0 to 0.5 radians per second may, now you have twice as many samples as you had earlier. Right? So the point is that as your time period increases, the frequency samples become closer and closer. Right? They become closer and closer. And similarly, I mean, this is for 16 times T1. Right? So capital T is now twice as much as it was earlier. So Daniel, T and T1 are here. So this is T1 and this is T. Okay? So T1 stays constant and I keep on increasing capital T, right? So as I keep on increasing capital T, the frequency content becomes closer and closer, or the stems plots becomes closer and closer, starts compressing. Ji, Umar.
Sir, is it always the case that higher frequencies have less contribution in a transform?
Not necessarily. So we'll talk about this. That's a good point here. We'll talk about this. So not all signals are like that.
Okay, sir.
Right? In this particular, so I think Umar, ये कहाँ से question आ रहा है? इसलिए क्योंकि आप देख रहे हैं कि low frequencies पे contribution
yes,
ज़्यादा
है.
Yes,
low पे peak higher है और बाकी फिर आहिस्ता-आहिस्ता वो decrease कर देता है right.
Excellent. Not all signals are like that. It's actually because of the nature of the square wave that you observe this phenomena. There are other signals out there in which it's maybe the other way around, as we're going to see later.
Okay, sir.
Okay, a good question. Now, so the point here was this is 0, this is omega naught, and here this would be 4 4 mega naught. So this would be A2 mega naught. This is A2 mega naught, right? So up, which is still, by the way, still 0.5 radians per second. So 0.5 radians per second may you have even more and more samples placed, right? And so as I keep on increasing t, मेरी frequencies में करीबी आना शुरू हो जाती है. Now, what happens in the limit? So here's the connection between periodic signals and aperiodic signals. Why are we doing this? How are periodic signals and aperiodic signals related? As I keep on increasing t, right? As I keep on pushing this further and further, दूर दूर करता जाता हूँ, दूर दूर करता जाता हूँ. What happens to this periodic signal? Does it not look more and more like an aperiodic signal? Is that true or not true? Okay, क्या ख्याल है? Right? So that's the point. So as I keep on increasing capital T, these frequency spacing, this frequency spacing between adjacent harmonics is going to start decreasing and decreasing, and they're going to come closer and closer and closer together as capital T keeps on increasing. And when does the periodic signal start looking like an aperiodic signal? That happens when capital T goes to infinity in the limit, right? So if I keep this infinity, तो ये सारे के सारे इतनी दूर, ये वाली pulse इतनी दूर चली जानी है कि it's no longer there, right? It's no longer there. As capital T goes to infinity, it's no longer there. And ultimately, in that limit, you just have a signal which looks like the square wave bus and nothing else. So this is T1 and this is minus T1, right? And as that capital T goes to infinity, right? What would you expect this frequency spacing to be? What would you expect this frequency spacing to be?
Sir, ये zero को approach कर देगी.
Zero को approach कर देगी. Excellent, Asad. Right? So it would approach zero, right? And therefore these harmonically related contributions would actually now take on values over a continuum of values of frequencies, right? And that's what is, I mean, that's the intuition behind how Fourier transform is derived. And that's actually how Fourier actually went about this derivation in the first place. He started from Fourier series and said, Keji, I want to generalize this to aperiodic signals, and not necessarily, because there are many, many signals out there which are aperiodic and of practical interest, right? And I would still want to express them as a superposition of the fundamental basic signals, which are the complex exponentials, right? I would still want to do it. And the way to do that is through this generalization, as we're going to try. So this is, I mean, this first few minutes that we spent, and this was a general intuition behind how Fourier transform is generalized from Fourier series, right? If there are any questions about the intuition, I'll take them. But otherwise, I'm going to start going into some mathematical analysis and dig a little bit deeper into this. Okay? And any questions before I dig into the mathematics? No. Okay. So once again, intuition is that in order to convert a periodic signal into an aperiodic signal, what we can do is we take the limit of the period going to infinity. And as that limit, in that limit, what happens in the frequency domain is that the harmonically related exponentials, they become closer and closer together to a point where the contributions are in fact not because of harmonically related exponential, but rather because of exponentials that take on values, frequency values, over a continuum of real values. So this curve is no longer going to be discrete, but rather continuous. That's where we're headed. That's what we want to analyze. That's what we want to derive. Okay? All right. If no questions, I'm going to go ahead and. All right. Okay, let me. All right, so this is where we start this analysis, which is development of Fourier transform from the Fourier series. Hassan, you said something about coming across something like this in your research?
Yes, sir.
एक मिनट में बता दें.
Basically the idea was कि हम लोग I deal with crystals, और crystals में जो ना periodicity होती है, because it's a periodic structure.
Yeah.
But if you want to make 2D layers of it, तो क्या करते हो आप वो एक layer लेते हो and then you move the other layers apart, right? To try to make it a 2D layer.
Okay.
अब उसमें मसला ये होता है कि if you use क्या कहते हैं waves, so you need an infinite amount of waves to model free space, empty space, बिल्कुल flat lines. तो वो computationally बहुत taxing होता है.
Okay.
So we came up with a bunch of approximations to try to keep that at zero, keep the space for a reason zero, and still be able to model the 2D materials.
Okay. लेकिन उसमें were these concepts of frequencies there? I mean, I'm trying to see, KD, was that related to the Fourier analysis somehow, or was that based on the approximation वाला जो?
It was, क्योंकि हम जो periodic जो चीजें होती हैं, हमारा जो crystal होता है, in real space we have these distances between atoms, but we don't look at it in real space. जब वो computer में हम लोग देते हैं, we look at the Brillouin zone. The Brillouin zone is in the frequency domain. K space में होता है वो.
Okay. Right, interesting, very interesting. चलें जी. So you sort of realize कि how far-reaching of implications does this analysis have, not just in engineering but also in basic sciences. Actually, basic sciences. So if you went through the video that Saeed shared, in शुरू वाला analysis, that was right from heat equations or वहाँ के differential equations के solution से. So it's actually science that actually drove this analysis.
That is actually why I took this course. My professor told me to.
Okay. Achari. So as I said earlier, I mean, the basic idea is, so once again, we want to try to express aperiodic signals as a superposition of complex exponentials. And the basic idea is, that aperiodic signals can be thought of as a periodic signal with this time period going to infinity. Right? Achha, by the way, I mean, if you have any answer to that, I mean, just type it up in the chat. Zoom is going to record these chats. I look at it later as far as the CP is concerned. So anything you want to say, I just tick mark. Check kisne chat mein type kiya tha. Something related to the course. Right. So, and for this, let me give you an illustration, right? So let's say there's an aperiodic signal, which is x of t. And what that looks like is the following, right? So let's say that's an arbitrary signal, which looks like this. Ye hai, and this goes up and something like this, right? This is x of t, right? Now there's, let me visualize a periodic counterpart for this signal, right? And that periodic counterpart for this signal looks like the following, right? So this is x tilde of t, right? And this x tilde of t has the same shape, except that we start repeating this x tilde periodically, right? With some period t. Yeah, and this. Right, so this is 0, this is capital T, this is 2t, and this is minus t, and so on and so forth. Right? And clearly what we see is kg, x of t is equal to x tilde of t as long as this t is less than capital T by 2. Okay, so within one period, x of t equals x tilde of t. And how are x of t and x tilde of t related? Can I say that they for some value of capital T, x tilde of t is going to approach x of t? What do you think? What is that relationship between x of t and x tilde of t? T going to infinity, excellent, right? So as in that limit, as capital T goes to infinity, right? X tilde of t starts approaching x of t. So I would say that x of t is equal to limit t going to infinity x tilde of t, right? So this is what I start out with. Right? Now let me just look at x tilde of t now. Because x tilde of t is periodic, right? That means it must have a Fourier series decomposition. Since x of t, x tilde of t is periodic, we can write its Fourier series decomposition. And I mean, the implicit assumption is that वो Fourier series decomposition इसकी exist करती है. I mean, it satisfies all of the Dirichlet conditions, so on and so forth. Right? We can write its Fourier series decomposition through the analysis and through the synthesis equation. Right? What are those? Those are that x of t, or rather x tilde of t, is actually equal to summation k going from minus infinity to plus infinity a sub k e raised to power j k omega naught t, where ak is equal to 1 upon t integral. Let's say this is from minus t by 2 to plus t by 2, x tilde of t e raised to power minus j k omega naught t dt. Just application of the Fourier series analysis that we know of, right? So let me look at this ak for now, right? So let's say this is equation 2 and this is equation 1, right? So from equation 2, can I say the following, that ak is actually equal to 1 upon t integral from minus t by 2 to plus t by 2, and instead of x tilde of t, I just write x of t. Does that make sense? I mean, why are they the same? Right. So can somebody explain to me why? Right. Omar?
Sir, so we're basically integrating from minus t by 2 to t by 2.
Yeah.
And in that time period, x of t, x tilde of t only occurs once, which is basically just the same as x of t.
Excellent. Right. So that, I mean, so I because I am integrating from minus t by 2 to plus t by 2, this is where I'm integrating, right? And here in these limits, x of t is equal to x tilde of t in these limits, or in this time duration. And therefore, I can just replace x tilde with x, right? Acha. So I can say, okay, since x of t equals x tilde of t for absolute value of t is less than t by 2. All right. I can further write this as follows, is 1 upon t, and this is minus infinity to plus infinity, and this is x of t e raised to power minus j k omega naught t dt. Why is this true? Why can I take this integral now from minus infinity to plus infinity? What do you think? So you look at this, x of t, right? what do you observe? Excellent, Abdullah. Right. So we see here this x of t is actually equal to 0 for all values of t that satisfy capital absolute of t is greater than t by 2. Okay? Because it's 0 everywhere else. So outside of this one time interval, this we assumed, so this is an assumption we're making, we assume that x of t is 0 outside of the interval from minus capital T by 2 to plus capital T by 2. Okay? And that's why I can just replace the limits from minus T by 2 to minus infinity and T by 2 to plus infinity, right? And once again, the reason is because since x of t equals 0 for all values of t that satisfy this. Okay. Now, this implies that ak times t is equal to something which looks like the following: minus infinity to plus infinity x of t e raised to power minus j k omega naught t dt. Right? I say, can you let this function be x of j omega, which is defined as an integral from minus infinity to plus infinity, x of t e raised to power minus j omega t dt. Right? If this is x of j omega, if this is the function x of j omega, what can I say about this ak times t? So let's say this is equation number 3. Right? Then 3 becomes, what does this equation 3 becomes as a function of? Okay, Ibrahim says a times, excellent, right? So anybody else who was not clear on, so this is ak times t is actually equal to that function x, but it's just that instead of omega, I have k times omega naught in that equation 3, and therefore this is what I have. All right. Now, if I now say, if I plugging equation number 4 in equation 1, right, what do I get? What I get is that x tilde of t, which was my periodic signal that I started out with, x tilde of t can be written as this summation k going from minus infinity to plus infinity, ak, right? And ak is equal to 1 upon t x of j k omega naught times e raised to power j k omega naught t. Right? So this is just replacing equation number 4 into the original analysis equation, original synthesis equation, right? So in other words, ये जो चीज़ है, I mean, all I've done is, okay, this is actually the AK that I was working with. Okay, so let me write down this clearly, right? So this is x tilde of t is actually equal to summation k going from minus infinity to plus infinity 1 upon t x of j k omega naught e raised to power j k omega naught t. Right, so just a sort of a different way of writing that Fourier series. I mean, all we're dealing with is the Fourier series for now, right? Okay. Now, the question here is, okay, so I'll replace this, do some other manipulations as well, right? So I say, could you since t equals 2 pi by omega naught, what we have is that 1 upon t is equal to omega naught by 2 pi, right? And therefore, x tilde of t becomes equal to 1 upon 2 pi summation k equals minus infinity to plus infinity. And this is x of j k omega naught, and this is e raised to power j k omega naught t times omega naught. Okay, just some basic manipulation. Right. What can I say now as capital T goes to infinity? Right? So let's say this is equation number 5. So as capital T goes to infinity, right? What happens? Excellent. So omega naught goes to 0. Right? If omega naught goes to 0, so Maz and Asad say that x of t go to 0. Take a moment to see, would that be really true or not? Okay, so you're assuming anything multiplied by 0 is 0. Right? That's not really true. Right? What if you're adding a lot of things?
I had a question.
Infinitely many times up. Then what happens? Maz, you had a question?
So as you said, omega naught goes to 0, but इसमें हमारे पास नहीं अच्छा वो एक ही पावर में ठीक वो तो 1 ही हो जाएगा. तो I think it should be 0, but आप कुछ कहने लगे थे सर, आप explain करते.
Right, you see, you are adding a lot of things up. Right? You see, there's an infinite sum here.
Yes, sir.
Right? Now, if you add things infinitely many times up, right, it may not be, I mean, you're adding, so essentially what you're saying is omega naught is very, very small, right? If omega naught is very, very small, I mean, this thing here becomes very, very small as well. But you're adding these infinitely many times up. And therefore, this may not be 0. This may
so
not.
Basically, sir, you are saying कि जब तक हम वो infinity तक पहुंचेगा t, we would already have a great amount of sum that would itself be infinity.
May not be.
मतलब would be very big.
May not be very big. I mean, you're taking up a very, very small number and you're adding it many, many times, and the result may turn out to be finite.
Yeah, well, finite. Okay.
Okay. I mean, does this look like something? कुछ कभी चीज देखी हो जिसमें the sum in that limit becomes something else? And we sort of did this, I think, somewhere. I don't know. कहाँ पे किया था? Shifting property में, yeah. Right, this infinite sum in this limit. Anybody?
Change of variables करते थे जैसे.
क्या use करते थे?
Change of variables.
The change of variables चले वो, I mean, I don't want to go into a lot of details, but intuitively, I mean, एक sum है, right? ये चीज है, ये signal है, ठीक है? इसको आप एक छोटी से, so this ये is changes around omega naught, ठीक है? इसको आप जो छोटा सा interval में लेते हैं, उसको weight से multiply कर देते हैं, and you find the area under this, and then you change here and you find the area under this, and you just keep on adding these areas of rectangles, right? Right. This is nothing but the definition of an integral, by the way. Okay, this is a Riemann sum, right?
Yes, sir.
Right, and I don't want to go into these details here. It turns out, omega naught to 0, and take my word for it, and we can discuss this offline, right? As omega naught goes to 0, we can say is that the 5 becomes an integral. Okay, 5 becomes an integral. And what we have is that x of t, which is actually equal to limit capital D going to infinity x tilde of t, which is equal to limit omega naught going to 0 of what? This k equals minus infinity to plus infinity x of j k omega naught e raised to power j k omega naught t times omega naught, or 1 upon 2 pi beta, sorry. And this is nothing but an integral from minus infinity to infinity of what? X of j omega times e raised to power j omega t, and the integral is over omega. And this is x of t. Right? So, I mean, barring this, how do we get this integral? I mean, so that's, I don't want to spend a lot of time on that. I mean, so intuition should be clear here. As omega naught goes to 0, this reduces to an integral. But what you've really done is, x of t, remember, was an aperiodic signal. And what you've said now is x of t is actually still a superposition of complex exponentials, except that those complex exponentials are no longer harmonically related, but rather they take values over a continuum of frequencies. Okay? So if I were to summarize this up, right? So what I am claiming here are the Fourier claims, which is an awesome result, which is if there's an aperiodic signal x of t, then I can say that x of t can be written as this summation. So let me use a different color here. Right? So in conclusion, I can say that this x of t can be written as integral from minus infinity to plus infinity x of j omega e raised to power j omega t. I am sorry, I missed a 1 upon 2 pi here. And this is 1 upon 2 pi d omega, where x of j omega was what? X of j omega was equal to minus infinity to plus infinity integral x of t times e raised to power minus j omega t dt. Right? So we say that this is called the synthesis, and this is analysis. Okay. Talha, 1 upon 2 pi analysis में नहीं था, if you recall, right? So with this above, कहाँ पे किया था? Yeah, here. There was no 1 upon 2 pi there, right? So this is Fourier transform. We say that these are Fourier transform pairs. Okay. Now, I just want to, I mean, थोड़ा सा इसके साथ में Fourier series का अगर मैं लिखता हूँ, so just so that we can make those connections here, right? I mean, and make those connections to exactly what we did on those slides in the beginning, right? So that intuition that we try to build, right? So Fourier series में क्या कहते हैं? We say कि जी x, let's say there's a periodic signal x tilde of t, that is equal to summation ak e raised to power j k omega naught t, where this ak was equal to 1 upon t summation over capital T of what? X of t e raised to power minus j omega t dt. Now, can you try to make a connection of x of t with x tilde of t? Remember, x tilde of t and x of t are actually the same as capital D goes to infinity, right? And I see what happens here. So this k equals minus infinity to plus infinity. What happens here what happens in this equation here? What happened in this equation here as capital D goes to infinity, right? What happens? Omega naught goes to 0. As omega naught goes to 0, आपके पास जो contributions, and because of the exponentials, they become closer and closer in frequency domain. And as capital D goes to 0, the contribution is there, not just because of discrete set of exponentials, frequencies and exponentials, but rather a continuum of frequencies. Okay, as capital D goes to 0, and therefore omega naught goes to 0, and that's why this summation becomes an integral. Okay, and this goes back to the first example that I showed you, right? So as capital D goes to 0, frequency करीब होती जाती है, right? Up to a point where they becomes a continuum, right? And similarly, there's an analogy between these two as well, right? And I mean, you see that they're very, very similar, except it's been normalized by the capital T, and the integral is from minus infinity to plus infinity. Other than that, they're more or less the same. Okay? So what can we say about this x of j omega now? What is x of j omega? So Daniel says something about Laplace transform, right? So we've not talked about the Laplace transform yet, but there is a connection of this with Laplace transform. It turns out that Laplace transform is a generalization of this Fourier transform, right? So Fourier transform is just one specific form of Laplace transform. I'm not going to go there yet, okay? So let's just look at what x of j omega represents. So Asad Khalid says, okay, it's AK. Okay, so Asad, यहाँ पे, I mean, what was AK? Intuitively, if you can try to explain to me, okay, what was AK representing? Asad, if you were to explain this to somebody and tell them क्या AK क्या होता है, right? So to a freshman, let's say, how would you explain AK? Okay, the magnitude, or I mean, उसकी strength, what does it represent?
So ये उसका amplitude बताता है, coefficient.
इसका amplitude बताता है.
सर जो हमारा बस coefficients आते हैं, like जो wave है.
Okay. Anybody else who would want to elaborate on this? Right? Somebody who's not spoken yet. Saad Raza.
Sir, I'm not sure.
Okay. Zen?
Yeah, I don't know how to put in the simple terms, but जो हमारे पास वो पैटर्न बनता है, जो उसका पूरा एम्पलीट्यूड यानी कि इन लेमैन टर्म्स जो बनता है उसका फॉर्मेशन होती है, उसके बाद लाइक सिंपल टर्म्स में तो वही हो सकता है, बट लाइक आई डोंट नो हाउ टू पुट दिस इन बिकॉज मैं खुद भी अभी सर वो सब कुछ प्रोसेस कर रहा हूँ. सो
anybody wants to put it more eloquently? Okay, what does AK represent?
Sir, it's the amplitude of every impulse.
Okay, is the amplitude of every impulse के बजाय कुछ और है क्या?
Harmonics.
Harmonics, right? So इससे पहले अब्दुल्ला बोला था, अब्दुल्ला निसार?
Yes, sir.
All right. So and then Umar said harmonics, right? So AK represents the contribution, as I think Hassan and Daniel as well as say in the chat box. A sub K represents the contribution that e raised to power j k omega naught t makes in the signal x of t, right? So I say that the x of t or x tilde of t can be broken down into a superposition of complex exponentials of multiple frequencies, right? बहुत सारी उसके अंदर frequency शामिल है, right? And a sub k represents कि जी kth harmonic की contribution क्या है? And when I say kth harmonic, that means a complex exponential that has a frequency of k omega naught, right? So therefore, a sub k represents the the contribution of complex exponential of frequency k omega naught. And that led us to that frequency domain analysis and saying कि जी अगर as I think Umar pointed out कि जी वो जो square wave थी उसमें high frequencies के magnitudes कम थे और low frequencies के magnitudes ज़्यादा थे, and that sort of let us visualize that signal in a different manner, right? In a different, with a different perspective, right? That the high frequency components have lower magnitudes and the lower frequency components have higher magnitudes. Okay. Now, similarly, can I make the same sort of analogy on this left-hand side with the aperiodic signal here? Can I say the same, e raised to power j omega t? I can still say x of t is made up of complex exponentials as a superposition of complex exponentials, right? So here I can say 1 upon 2 pi times x of j omega times d omega, right? That represents the contribution of a complex exponential of frequency what? Frequency omega, right? And here, this omega is on the real number line, as opposed to in the periodic case. Here, this was as I move k over the integer set, the frequencies that I traverse are not the entire number line, but a discrete set of frequencies on the number line, on the real number line. ठीक है, उसमें the discrete set आता है, as opposed to in the periodic case where there are that takes on values, it could take on value over a continuum of values on the real numbers, on the real number line. Okay? So this is, so x of j omega is related to the contribution that a frequency of omega has in my periodic signal. And how do I find x of j omega? I find this x of j omega through this analysis equation. Okay? Any questions here? And we say, okay, this is the Fourier transform of x of t. I mean, just like you would have been familiar with for Laplace transform, this expression here represents the Fourier transform of the signal x of t, where now the independent variable in this transform is not t anymore, because t is something that you're integrating over, but rather omega. I mean, it says how does the contribution change as a function of the frequency, right? And this, the equation up above, which is a synthesis, is often called the inverse Fourier transform. Okay, if you're given the Fourier transform, how can you determine the time domain signal? You can determine the time domain signal through the inverse Fourier transform, and it's called the Fourier transform pair, as it's often called. Okay. Daniel, let me take your question first. You said, how did you get this expression? Which expression?
Sir, 1 over 2 pi x of j omega.
Okay, so here's how. So let me expand on this here. So I know x of t equals 1 upon 2 pi integral from minus infinity to plus infinity x of j omega e raised by j omega t d omega, right? So I can say this is actually equal to 1 upon 2 pi x of j omega and e raised to power j omega t and times d omega. So what is the term which is being multiplied by e raised by j omega t? Daniel, ye term hai na? This and d omega, right? So this is being multiplied by e raised by j omega t, and then you're integrating, which basically corresponds to a sum, right? Just like yahan pe ak was a term which is being multiplied by e raised to power j omega t, okay? I've tried to bring that analogy here. That's how I do this. Daniel, is that clear?
Yes, sir.
Okay, the summation is no longer a summation, but rather an integral, right? Integral क्या होता है? Integral is a limiting form of a summation, right? So what is the constant which is being multiplied by e raised to power j omega t? This yellow constant is being multiplied by e raised to power j omega t, and I multiply this constant as a function of omega with every e raised to power j omega t, and then just sum everything up. That's why I say okay, the contribution that's there because of a particular complex exponential e raised to power j omega t is this yellow term. Okay? Now there was another question by Talha. Talha, unmute करें.
Yes, sir.
You're saying कि जी is the same as the Laplace?
Yeah, मैं ये पूछ रहा था because j omega is also complex frequency and Laplace में भी हमारे पास complex frequency होती है.
Yeah.
S. So how is it different from that?
उसमें Laplace में S में real part भी होता है, remember?
Okay, yeah. तो यहाँ पे it is purely complex.
यहाँ पे real part नहीं है. Right? So we're going on a tangent here, but Laplace is evaluated on the S plane, which has a real axis and there's an imaginary axis. अगर वहाँ पे S equals j omega ले लें, so then Laplace transform actually reduces to Fourier transform, and there's a very nice relationship between the two. Okay, so in conclusion, this synthesis expression and this analysis expression, this is the key, right? And which is used very, 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 very beneficial, right? As far as engineering applications and scientific applications are concerned, right? So let me just box this up. So these are the two important. So if Fourier transform and inverse Fourier transform, okay? Fourier transform and inverse Fourier transform. Any questions before I do some examples? So conclusion is, okay, we started out with Fourier series, right? Because that's something we knew, right? And then from Fourier series, we try to generalize that analysis for aperiodic signals. And from that generalization, from that analysis, we found out, okay, x of j omega is something called the Fourier transform given by this analysis expression that you see on your screen, right? And we can then therefore view x of t alternately in the frequency domain, x of j omega. What does that mean? Let's talk about some examples and see कि उसका क्या मतलब क्या है. Right? Any questions? All right. So here are some examples. So remember, we're dealing with aperiodic signals, right? So x of t equals e raised to power minus a times absolute of t, right? This is a signal that we're dealt with, we're given, right? And for this signal, what you're required to do is to compute the Fourier transform. Okay? Now, what would the Fourier transform tell you? Let's compute it first, and then we can talk about that, right? So first off, is x of t, if I were to sketch this out as a function of time, if this is t, this is time, this is x of t, what does its signal look like? What does its signal look like?
Sir, mirrored version होगा एक decaying exponential का.
Decaying exponential. Why do you say it's a decaying exponential?
Sir, minus a, अगर a positive है तो.
अगर a positive है, right? So that's important here, right? If a is positive, that's when it was going to be a decaying exponential. Otherwise, it's going to be a growing exponential, right? So for a is greater than 0, it is a decaying exponential on both sides, and it's symmetric around t equals 0. This is, I mean, clearly it's an even function. Okay, so this is what it looks like. Something like this. And at time t equals 0, the value here is 1. Okay, now you're required to compute the Fourier transform, right? So we say compute x of j omega. Okay, what is x of j omega? So x of j omega is equal to this integral from minus infinity to plus infinity. This is x of t e raised to power minus j omega t dt. So therefore, this is integral from minus infinity to plus infinity, e raised to power minus a absolute value of t, e raised to power minus j omega t dt. How do I evaluate this integral?
सर सिमेट्रिक है तो हाफ करके डबल कर दें.
Symmetric. Why do you say it's symmetric?
सर क्योंकि इवन फंक्शन है ना.
Right. लेकिन अगर ये टर्म ना होती, that's when it would have been symmetric. Right? But you have e raised to minus j omega t. Minus e raised to minus j omega t is not a symmetric term. Right? So e raised to minus j omega t is not even. So therefore you cannot split it up and multiply by 2, but you would have to split, right? So I split it up in the sense that I integrate from minus infinity to 0, and you have e raised to minus a absolute of t times e raised to minus j omega t dt, plus integrate from 0 to infinity e raised to power minus a absolute of t e raised to minus j omega t dt. So e raised to power minus a absolute of t for all negative values of t is equal to what? And Hassan already points to this in the chat box. So this is minus infinity to plus infinity. Oh, sorry, to 0. So for all negative values of t, absolute of t is just equal to minus t. And therefore, this is e raised to power plus at times e raised to power minus j omega t dt plus 0 to infinity. All positive values of t, the absolute of t is just equal to t. So therefore, this is e raised to minus at times e raised to minus j omega t dt. And therefore, this is minus infinity to 0, e raised to power a plus j omega times t dt plus 0 to infinity e raised to power minus a plus j omega times t dt. And then it's just a simple matter of computing this integral. So this is 1 upon a plus j omega times e raised to power a plus j omega t. G Hassan? Hassan, you had a question?
सर नहीं, वो बस आपने a plus j omega लिखा है.
Oh, sorry.
a minus j omega.
सर आप ये बता देंगे कि उधर नेगेटिव टी का एब्सोल्यूट हमने नेगेटिव टी क्यों लिया है थर्ड लास्ट स्टेप के अंदर?
Okay, so how do you define, what is the definition of the absolute value? So I say that the absolute value of x is equal to, because we're dealing with t, let's do that with t. Absolute value of t is equal to minus t for all values of t less than 0 and is equal to plus t for all values of t is greater than 0. That's the definition of absolute, right? Right, so this is, if this is t, this is absolute value of t. Right, what is the absolute value of minus 2? So Asad, what is the absolute value of minus 2?
So minus 2 ही होगी.
The absolute value of minus 2.
Sir, absolute value of -2 नहीं रहेगी.
नहीं, absolute value -2 is +2, right? Yeah.
ठीक है.
Absolute value is +2, and therefore any negative value that you have, उसका absolute value is just the -1 multiplied by whatever the value was. ठीक है? So the reason why I do this is because of this definition of absolute value. Okay. So Abdullah ने भी हाथ खड़ा किया था, मेरे ख्याल में मेरी गलती निकाल रहा होगा. Right? So and this is 1 upon, यहाँ पे भी गलती है मेरे ख्याल में. नहीं, this is minus j omega. This is 1 upon a plus j omega. This is e raised to power minus a plus j omega. And this is 0 to infinity. So I've just flipped the limits because I've incorporated the minus sign inside the limits. Okay, it's fairly simple, right? So this becomes equal to 1 upon a minus j omega plus 1 upon a plus j omega, which is equal to, this is a squared plus omega squared, and this is 2a. Just some manipulation of complex numbers. Okay, a minus j omega times a plus j omega is a squared plus omega squared, right? Ji Talha.
ये आपने सेकंड में infinity to 0 किस तरह गए हैं?
Sorry?
आपने जब यहाँ पर after integration you wrote it infinity to 0.
Yeah. Minus infinity
नीचे
in the second?
वो first में, yeah, second में, yeah.
यहाँ पे?
Yeah, जी.
Because there was a negative sign here, I just incorporated that inside the limits.
Okay, वो after जब हमने ठीक है, after integration we got negative.
Yeah. ठीक है. All right. So let me write down what the conclusion is. The conclusion is the following: that if x of t is equal to e raised to power minus a absolute of t for a is greater than 0, if I compute the Fourier transform for that, I say if I compute the Fourier transform for that, the Fourier transform turns out to be, as we've computed, turns out to be equal to 2a divided by a squared plus omega squared, right? And if I were to sketch this x of j omega, right? So let's try to sketch this x of j omega. So this is omega, right? Because now omega is the independent variable as far as the function or the signal, the function x of j omega is concerned, right? You have, this is x of j omega, and the function will look something like this. Right, so it will decay as omega increases, right? And here is going to be, this value here is going to be 2 divided by a. All right. Now, on the other hand, the time domain signal, which is t here, this signal is an exponentially decaying signal, right? Where the height is 1. So this is the Fourier transform relationship between the two. And these are called the Fourier transform pair, right? Now, the question here is, कि यार इसका क्या मतलब क्या है? And what does this, when you look at this x of j omega, remember, there's always a one-on-one relationship between x of j omega and x of t, right? So you have this x of t here. So when you look at this x of j omega, what does this mean? So what does this, for example, this value, this particular value of x of j omega, ये जो height है, ये क्या बता रही है आपको? What that means is that the value of x of j omega evaluated at this frequency here tells you what the contribution of the complex exponential of this particular frequency has in the time domain signal, right? So the time domain signal is made up of a composition or a superposition of infinitely many complex exponentials of different frequencies, right? And this gives you an idea of what the contribution of those complex exponentials are as a function of frequency. And we clearly see, as we saw earlier as well, okay, the contribution because of the low frequencies is higher compared to the contribution of the as compared to the higher frequencies. Okay, right? And this sort of tells us कि यार इस signal में high frequency components कम है और low frequency components ज़्यादा हैं, and this is sort of a low pass signal, if you will. Okay, just like that. If I'm speaking, right? So I mean, the easiest connection that you can make is with speech, right? So have you heard of कि speech की frequency composition क्या होती है, या spectral composition क्या होती है, या audible frequencies क्या होती हैं? Any ideas, or somebody can shed light on that? Ever heard of that? 2 to 20
audible range का सुना है, 20 hertz से
राइट. सो ऑडिबल रेंज आपने सुना है कि जी 20 हर्ट्ज 20 किलोहर्ट्ज होते हैं typically, right? Even though E100 we did that जी, you may not be able to actually hear because you're now not so young anymore, right? So you may not be able to hear 20 kilohertz anymore. So you can do that MATLAB. Then do that test in MATLAB and see कहाँ तक सुन सकते हैं, कहाँ तक नहीं सुन सकते, right? But at the same time, audible के अलावा human speech भी है. Human speech actually goes up to 4 kilohertz. Approximately 4 kilohertz, right? इसका मतलब क्या है, right? Similarly, if I speak as opposed to, for example, my daughter speaks, who's very young, right? What do you expect कि मेरी आवाज और उसकी आवाज में क्या फर्क होगा? Anybody?
Pitch का sir.
Pitch का, excellent, right? So pitch का फर्क होगा, right? So her voice is going to be at a higher pitch compared to my voice, right? But what does higher pitch really mean, right? Pitch is related to frequencies actually, right? So now I can tell you this. So once you're familiar with this Fourier transform, what that means is if you take Hanya's voice, who's my daughter, right? And take the Fourier transform of that, and you take my voice and take the Fourier transform of that, you will find that the Fourier transform of my voice is concentrated more at the lower frequencies compared to Hanya's voice, whose Fourier transform is going to be concentrated a little bit more at the higher frequencies, right? And so Fourier transform really tells you कि यार जो speech signal है उसकी frequency composition क्या है, right? And that is an extremely powerful tool, as we're going to see in some application later on as well, right? So in practical world, speech signal, you can make those connections. What would Fourier transform applied to a practical signal like speech mean? That means is the speech that's coming out is actually made up of complex exponentials of different frequencies, and the Fourier transform tells me कि इस speech signal के अंदर कौन सी frequencies की क्या contribution है, किसकी ज़्यादा है, किसकी कम है, right? Now, as far as this signal is concerned, this is a very elementary signal, right? So we're starting out with elementary signal. And you can have the same analogy here as well, which is if you were to take up complex exponentials of frequencies from -infinity to +infinity and add them up or integrate them up in a particular fashion so that as this omega goes on from -infinity to +infinity, uske weights आप adjust करते रहें based on what this tells you. You start adding them up, you integrate them up, what you're going to get is this here. Okay? And as you can see over here, the high frequency components are weighted more as compared to the lower frequency components, right? Now we can see what happens as I change A, right? As I change A. So what happens when omega or A increases, right? So that'd be, so when A so increases, what happens? जी तलहा
अभी आपने कहा था हायर फ्रीक्वेंसी आर वेटेड मोर, तो किसमें हायर फ्रीक्वेंसी ज्यादा वेट हो रही है?
वो मैं I was talking about speech, right? So when I was talking about my voice, my speech versus my daughter's speech. ठीक है, तो आप उसका Fourier transform में, and I'll share those. I'll put this article up in the tab, lessons tab, where I will actually give you the Fourier transforms of my speech versus Hanya's, and you will be able to see the clear distinction. Okay.
यहाँ पर तो अभी जो हमारे पास सामने है, इसमें तो your frequencies are being weighted more, right?
Exactly. Lower frequencies are exactly. So lower frequencies have a higher concentration, and the higher frequencies have a lower concentration. Okay, lower amplitudes, if you will, right? Acha. So in order to answer this, let me take two cases, right? So which is, yeah, let's say this is t, this is x of t, and let's say A was equal to 0.1, right? So what kind of a signal would you expect in the time domain? So that signal is still a decaying exponential, but the decay rate is very, very small. Something like this. Right? As opposed to another signal. Let's say this is t, and this is x of t, but here A is, let's say, 10, right? This will have a much, much faster decay, right? This is A equals 10. And this here would be, किस तरह का signal होगा? Something which goes down to 0 very, very quickly, right? Maybe much, much steeper than that, right? Now, what can you say about the two signals? Is the signal corresponding to A equals 0.1 smoother, or the signal corresponding to A equals 10 smoother? Right, 0.1 is much, much smoother, right? A equals 10 has a much sharper decay, starts at 1 and very, very quickly decays down to 0, right? So there's a very, very steep transition, right? As opposed to A equals 0.1, there's a very, very slow transition from up above all the way down to 0. Okay? Now let's look at what the Fourier transforms are, right? So iska Fourier transform agar main loon, if I compute the Fourier transform for that, what I am going to observe is, if this is omega and this is x of j omega, right, which is still equal to 2 times a divided by a squared plus omega squared, right? उसकी shape जो है क्या होगी? उसकी shape जो है would be something like this. Oh, sorry. So a is small, right? And therefore this would be something like this, right? As opposed to this case here. So this is omega, this is x of j omega, and this is going to be like this. Right, it's not to scale. The y-axis is not to scale, but the x-axis is to scale, right? So x-axis may, there's a much, much larger spread of frequencies, right? Because A is very, very large. If A is very, very large, so omega squared ka effect kam hai, right? As omega increases, the spread is increased. And you can verify this as well when you plot it out, right? So, and this makes intuitive sense, by the way. I mean, how does it make intuitive sense? क्या ख्याल है जी दानियाल?
सर A is equal to 10 वाले पे क्या कहते हैं काफी ज्यादा different frequencies की sounds होंगी तो वो like noise से लगेगा.
So excellent, but Daniel, we're not talking about speech yet or sounds yet. Okay, this is just some arbitrary signal out there, right? And so we say KG for A equals 10. I mean, the contribution is sort of uniform for a lot of frequencies, and as the low frequencies contribute almost as much as the high frequencies. Okay, because the decay is much slower, right? As opposed to A equals 0.1, where the decay is very sharp in the frequency. ठीक है, और इसका मतलब हाई फ्रीक्वेंसी जो लो फ्रीक्वेंसी कंपोनेंट्स की जो कंट्रीब्यूशन है दैट इज मच मोर सिग्निफिकेंट कंपेयर टू द लो फ्रीक्वेंसीज. ठीक है, व्हिच मेक्स सेंस बिकॉज द टाइम डोमेन सिग्नल इज मच स्मूदर, उसमें जैगेडनेस बड़ी कम है, right? इसलिए वो लो फ्रीक्वेंसीज कॉरेस्पॉन्ड्स टू द स्मूदर सिग्नल्स, हाई फ्रीक्वेंसी कॉरेस्पॉन्ड्स टू शार्प ट्रांजिशंस. ठीक है, so everything makes intuitive sense, right? So the Fourier transform allows us to, in summary, to visualize time domain signals in the frequency domain and see कि the frequency domain में किस frequency content की contribution ज़्यादा है, किस frequency content की contribution कम है, right? And quantify them, right? So this is where I'll stop. Let me know if you have any questions. जी Daniel.
Yeah.
सर तो बेसिकली अगर हम स्पीच के टर्म्स में बात करें तो इसका मतलब ये है कि एक स्पेसिफिक इंस्टेंट पे टाइम के जो जे ओमेगा है, मतलब ये पूरी एक स्पेक्ट्रम ऑफ फ्रीक्वेंसीज है जो उस साउंड में है. मतलब इसका मतलब ये है. अच्छा सर, मेरा एक और क्वेश्चन था कि अक्सर हमने देखा है ऑडियो प्लेयर्स वगैरह पुराने जो होते थे उसके अंदर होता था कि म्यूजिक चल रहा होता था तो साथ एक वेव फॉर्म सी बन रही होती थी. और उसमें नोट किया कि जो हायर फ्रीक्वेंसी साउंड्स होती हैं उसमें राइट साइड पे काफी ज्यादा आते हैं, पीक्स आते हैं, तो वो Fourier transform थी इसकी.
Yeah, so what they were showing you is a Fourier transform of the audio signal, which is a time domain signal.
Okay,
तो यहाँ पे दानियाल कभी आपने वो देखे since you talked about those cassette players or audio systems, एक equalizers होते थे, right, which were actually knobs, right? And on top of those knobs you had frequencies written down.
Yes sir, I know about equalizers,
right? So that's nothing but the Fourier transform. What you're saying is you take the Fourier transform and just amplify some of the frequency content more than the others.
Yes sir, makes sense.
So vocals are at lower frequencies, or bass or the drums, and there are much even lower frequencies. If you want to amplify the drums, so you just amplify the low frequency components compared to the high frequency components, and that's equalization. The basic tool is Fourier transform. जी तलहा.
Sir, can you repeat this last part जो आपने भी बताया था इसके बारे में about how is A की value change करने से क्या हो रहा है?
You see, so the pink signal, right, is A equals 0.1. In the time domain, it's a much smoother signal, right? And in the frequency domain is the other way around. It's a frequency domain, it suddenly drops down to 0, right? So decay is much faster, as opposed to A equals 10, where the time domain signal is the decay is much faster, drops down 0 very quickly. But on the frequency domain, it's the converse. It's the other way around. The decay is much smoother, right? What that means is the signal at the bottom, right, which is the green signal, has frequency components which are distributed over a larger range of frequencies, right? So the contribution because of the high frequencies is almost comparable to the contribution because of low frequencies, right?
This is for the high value of A.
Yeah, this has a much wider spread here as opposed to this spread here.
अच्छा, इसमें A, what exactly is A here?
Sorry, फिर से कहिए.
A क्या है exactly इसमें time domain में?
Time domain में is a
constant.
Is a constant. Is a decay rate कहते हैं इसे.
ठीक है.
Right. So and so the point here is that the spread here is a lot smaller than the spread here. Right? Which makes sense कि इसमें नीचे वाले के अंदर ज़्यादा free high frequency content मौजूद है compared to the top signal because it's not as smooth.
And इसके बाद जो दानियल से आप बात कर रहे थे about that frequency जो the spectrum show करता है, how is that working? Like उसमें your frequencies are on the left side and higher on the right side.
Yeah. How is it?
That's how it's just working.
Yeah. So this
तो
is.
आप दानियल को कह रहे थे ना?
वो डिस्प्ले वो so वो एक पॉइंट रेज हुआ था कि जी when you're playing an audio or playing a music, right, उसका spectral analysis भी होता है real time में. Some plugins allow you to do that. Which tell you कि इस
sir, I can actually अभी मेरे पास वो मेरे desktop पे है, I can show you that.
Yeah, so for frequency content change हो रहा होता है ना, which you and on the x-axis you will see the frequency in hertz.
Yeah, well, actually, so I have it on my desktop and always. So, like if I play it from 20 hertz to 20,000 jain, so it starts on the extreme left, and it moves through the x-axis.
Yeah.
So, and amplitude almost remains the same.
Then
how is that related to
amplitude? Would not remain the same.
अच्छा वो मैंने check नहीं किया.
So how do you mean?
What I mean is the central amplitude.
Yeah.
As it moves through, so the shape remains almost the same.
Okay.
I look into it. You think how is it related to time domain?
So time domain is that's what there's a one-on-one relationship between the time domain and the frequency domain, right? So time domain may, if you're saying that frequency domain may, if you're saying that the high frequency content is smaller and the low frequency content is higher, what that means is the exponentials that make up the time domain signal, उनके amplitudes low frequencies पे ज़्यादा है, high frequencies पे कम है. That's the interpretation. Okay. So Daniel, you had raised your hand, right?
Yes, sir. Sir, मेरा एक और क्वेश्चन है इसी के मुताबिक. सर ये जो x of t है मुझे समझ नहीं आ रहा इतना बस कि अब ये भी एक टाइम पे डिपेंडेंट है. तो लाइक अगर हम स्पीच टर्म्स में देखें तो x of t कैसा साउंड करेगा? लाइक y एक्सिस पे इसकी लाउडनेस है या पिच है या क्या?
If this was an audio signal, which it may not be, but if this was an audio signal, then the y-axis would correspond to the loudness of the audio signal.
Okay.
उसका volume.
लेकिन सर अगर यही लेकिन ये डिपेंड भी करता है ना कि किस बंदे ने बोला है ये बात. अभी कोई श्रेल आवाज वाला कोई बंदा करेगा तो जो ट्रांसफॉर्म है वो राइट साइड पे शिफ्ट हो जाएगी मतलब.
या वो लेकिन वो फोरियर डोमेन में राइट साइड पे शिफ्ट होगी. टाइम डोमेन में जरूरी नहीं है.
सर बेसिकली टाइम डोमेन में दो सेम सिग्नल्स जो हैं उनकी अलग-अलग फोरियर ट्रांसफॉर्म आ रही है.
No, so there's a one-on-one relationship between the time domain and the Fourier domain, right? So if you have the time domain signal, if you two time domain signals which are different, then the Fourier domain would also be different. One-on-one relationship.